You know, a large part of chemistry, why things react the way they do, it has to do with electrons. And electrochemistry is really an important chapter to cover. We get to it in AP and honors. I think a good part of it could be taught in traditional chemistry as well. What is electrochemistry? Well, we talk a lot about reduction potentials. What it really boils down to is a kind of a tug of war. That's the best analogy I can think of. The ions have different tendencies to attract electrons to them. And when you pair them up one against another, we got a chart over here that shows several reduction potentials for 6 common metals: copper, lead, tin, iron, zinc, and magnesium, all 2 positive ions. And these are all the reduction half reactions, and these are the standard reduction potentials. What does that mean? Well, you could think of that as that is the tendency of, or strength of that ion to pull electrons toward it. And if I were to pair up any of these 2 ions, copper against lead, copper against tin, I could see that copper, 2 positive, would be pulling electrons toward it compared to any of these other ones. These are ranked from highest to lowest. Where are those numbers coming from? It's just arbitrary. They set hydrogen ion as the 0, and these are all just relative to that. So we've got a little activity here where I've got these exact same 6 metals as unknowns labeled A, B, C, D, and E. And my students start by making a prediction. Here they are. I'm missing one? Oh, I am. They look at them, they feel them, they pick them up, they try flexibility, and they make predictions as to which ones they are. Okay? They're in containers that are labeled A, B, C, D, E, F, so they write that down as they pick them up. Once they've done that, here's what they do. They have to buff them because a lot of them have oxide coatings, and to buff them you just take a piece of steel wool and rub it across there. And then they take a piece of filter paper and they cut little wedges out of it. And I have an example of this for them to do. And they're trying to make 6 little petals, like a little flower. Okay? And when they're done, they'll have something looking like this. Doesn't have to be perfect. Then they have to make 2 little slits near the edge of each of these. So they fold it in half a bit and make 2 little cuts like that. And so you get the little slits there. That done in each one of the 6 petals. And when they're done, they'll label them A, B, C, D, E, F with a pencil or a marker that's not going to run. And then they slide the metals through those slits. So A gets slid in there and so forth. And of course it looks like this, all shined up and ready to go. Okay? I can see my A has even oxidized a little bit since the time I buffed it before I set this up. So they're good to go now. And I'm good to put on my goggles because now the chemicals come out. Well, you could argue the metals were chemicals to begin with, but now the solutions come out. And we've got a little voltmeter here. Okay? And I'm going to start, though, by taking about 4 or 5 drops of each of these solutions. The first is potassium nitrate. And by the way, what I've got here, what I'm constructing, are a bunch of galvanic cells, complete with salt bridge. And I'm doing it with all possible combinations at one time. The setup we see in the textbook of the electrodes put into the solutions, a copper electrode put in a copper solution, zinc electrode put in a zinc solution, a salt bridge. You can simplify that quite a bit and go with much smaller quantities. These are all 1 molar solution. Here's my potassium nitrate, which is going to be the salt bridge in the middle, and I'll put 1, 2, 3, 4, 5 drops of that. Here's some solution A. They're unknowns. A goes with A, so we're going to put 5 drops of that here. B, let's see, where's my solution B? Goes here. And you're saying that's not enough. It's not. They're starting to meet here. That's all you need. It's just enough for them to make contact. Solution C goes on C. D on D. on E and F. You kind of have an inkling of what F is there, and this probably helps you, knowing that the F solution is colored. So we got 5 drops of that there. Okay? Now, they're still migrating a bit. I might put an extra drop or 2 if I see they're not going to get there quite. Maybe 1 more drop of B here. And now we're ready to go. And I'm going to start by turning on the voltmeter. Okay? And then it's 0. And what I'm doing is I'm essentially going to pit these up, these metals, these solutions actually, up against each other, 1 against 1. Let me have 1 more drop of D, just because I can see it's taking a little time to absorb, and maybe C. The rest look like they've all made contact. And C probably would have too. Okay, so we're going to pit these up against each other, and when I put the black electrode on one, and I'm putting it right here, couldn't be easier, and the red electrode on the other, what I'm assuming is electrons are flowing from the black to the red. If they're flowing the other way, it's okay. I'll just get a negative reading here. So this is indicating to what extent, with what force, driving force, electromotive force, the electrons are flowing from the black to the red. But if they're flowing the other way, if A is the better tug of war, then it'll just be a negative, and I could switch them or just take the negative reading. So we're going to have black on, and we have a person recording this on the board there. So here's our first voltage, A compared to B, and we're getting a negative 1.12. Okay, if I switch those, what do you think is going to happen? I should get a positive, right? Same voltage? Well, close, 1.09. I moved it a bit, and if you're not making the same contact, 1.09, yeah, negative. Okay. A and C. So here's, again, I'm always going to keep the black one on A, so we're consistent. And I'm trying not to get in the way of the voltmeter there. Positive this time, 0.11. It's kind of fluctuating between 1.1 and 1.0. AD, positive 0.18. So in this situation, the electrons are flowing from A to D, but with not a strong force. AE, negative now, 0.42. And AF, a positive 0.57. Now, I could then, and I have the students do this, they continue then. They put the one here on B and go around like that. I really don't need to do that. I can figure out which is which just based on all the competitions with A, because this told me not just which one won, but by how much it won, right? So we'll stop with that. But which two, just to see which two are the closest in terms of their thing, I think that would be C and D. So we'd expect, if I hook these up to C and D, if I can get a reading here, a very small voltage between these two, only, there it is, negative 0.07, which is exactly how far apart they are there. It's nice because it confirms it in a lot of different ways. So now how do I use that to figure out which one's which here? Let me borrow that chalk there. Thank you. I like using like a little number line here. And we're just assuming that this whole thing is based on the idea that A is our 0. And we'll just line them up. So if A is 0, B is negative from there, way down here, 1.12. C, positive 0.11. Okay, is this making sense? Hope it is. D would just be a tad bit above that at positive 0.19. 0.18, sorry. E, negative 0.42. And finally, F. Okay? Apparently the strongest of them all, way up here at a positive 0.57. Remember, these are the ions we're talking about. The most reactive ion, the ion that was pulling electrons toward it the most, apparently, then was F. So, back to my chart here, these are already ranked from strongest electron puller to weakest, the ions now I'm talking about, it looks like it makes sense that F would be copper, and then D would be lead, so we'll just line these up. I'll bring this with me if that's okay. So we have, this is our copper ion, this is our lead, and of course if it's the ion, it's also the metal that went with it. And then this is our tin. And look at this. We got the tin and lead, we're very close together, and look at this, tin and lead, very close together. Now these should just be 0.01 apart, and they're actually 0.07. There's some problems with the oxide coatings and that form. This is, of course, under perfect ideal conditions, but at least the hierarchy works. A would then be iron. E would be zinc, and solution B, magnesium. Okay? And that is a nice little way of showing. If you build like a little tug-of-war competition, it's a nice way of showing the electromotive sequence, the electromotive series, and does a lot to explain what electrochemistry is really all about. It's an electron tug-of-war. Thank you.
Let's see what happens when we make a battery here on this piece of paper. So we have a copper, and we're adding a copper nitrate solution around it. And we have zinc. And the zinc nitrate solution we're going to add around that. And in the middle we're going to put potassium nitrate. So now we have a potential difference between the two metals. If we put our voltmeter probes on each metal, you see we get a voltage. Here we have the red lead on copper and the black lead on zinc. If we reverse them and put the red lead on zinc and the black on copper, we get a negative number. What we want in a spontaneous reaction is a positive value. So if we reverse the probes, we get a positive value with copper on the red lead. How I remember what's been oxidized and what's being reduced from an experimental standpoint is reduce red cats. To me that means reduction takes place at the cathode, and that's the red lead on our voltmeter in this battery. So copper is being reduced. Now that you know how to make a voltage cell, what we're going to do is do 4 metals at one time and look at activities as well as voltage. So you have copper nitrate around the copper, you have silver nitrate around silver, zinc nitrate around the zinc, and lead nitrate around the lead, with a space in the middle for your salt bridge of potassium nitrate. Now what I want you to do is to record the voltage with each metal in this series and what color probe is at that metal. So here we have copper and silver. Notice the silver was on the red. Now we have copper and lead and the voltage. We have a positive value with the red on copper and the black on zinc. Red on silver, black on zinc. Red on lead, black on zinc. Red on silver and black on lead. Now what you need to do is to write half reactions for each of the reactions that you've seen here and calculate the voltage and compare that voltage to your theoretical values.